Hello everyone, and welcome to another session on the course line commutated and PWM rectifiers. And today is the last week we are going to talk about the concluding parts of this course. And today we will talk about the battery energy systems. Okay, basically we will talk primarily of the converters which we use for battery storage systems. And since this is a we charge the battery from the grid, so basically the converters that we use are basically some form of a rectifier when we charge the battery, and when we discharge the battery from the grid to the from the battery to the grid, then it acts like a inverter. So basically we need a bidirectional converters. So this is what we will talk about in this week 12, and we will also talk a little bit about electrolyzers. Okay, this we have not included in the total course content, but I thought that maybe we should have a little bit of introduction, probably half an hour, just to give you a flavor of electrolyzers as part of the PWM rectifiers. The reason why we have included it at a later stage is because of the fact that we see that the hydrogen production and use of hydrogen as part of grid support, for various features of grid support, that is going to play a very important role in near future. Also for production of hydrogen and being used in a fuel cell as part of the transportation sector. Those are very important applications of hydrogen, upcoming applications, and so that's why we have included this electrolyzer as part of the course, just briefly at the end of the course. So let us talk first about the battery storage system. This is what we will now talk about. So what we see here is that battery storage system, we know batteries have been there for a long time, and they have been used. We use batteries every day. For example, our mobile phones have a battery inside, so we use them every day. However, here we are talking about battery storage systems for on a much larger scale. Okay, so this is like grid. The battery energy storage system is used at the grid level for supporting the grid. Okay, so because where do we see the maximum application is where there is a lot of renewable energy production. Okay, so in a renewable energy systems, the although it is very fine, like we have solar and we have wind and all, but one of the most important nature of this renewable energy source is that they are intermittent in nature. Okay, so we do not get the solar at night time, we do not get wind all the time at the same rate. So therefore we need some form of a storage system, and this is typically a battery energy storage system, to have a stable and reliable power being dispatched to the load. Okay, so this is where the BESS, or battery energy storage system, becomes very important. Okay, basically so in this course, or in this part, we will mostly talk about the power converters which are used for BESS, not as a general what are the different technologies or what are the different cell chemistries. Those things we will not talk about, we will just briefly mention them. So if you see the electrical point of view, so this is the battery pack here. Okay, and as I told you, we need so we have the cells or the battery pack, right? And we have a DC to AC converter. This is a DC AC converter, but this is bidirectional. Okay, this is bidirectional because we need to charge and discharge the battery. and then we have a transformer and we have a grid. Okay, so this is the transformer, and of course we want to interface with the grid, right? The transformer is needed from isolation standards which are necessary. Okay, now what are the typical voltage and powers we are talking about? We have a slide at the end, but just to give you a brief idea, the voltage of the individual cells are actually pretty low. Okay, maybe like 3 to 4 volts per cell. Okay, so it's not very high, and but we arrange them in series and parallel battery cells. Okay, and we make the battery bank, right? This is the battery pack or battery bank. Okay, so we make a lot of cells connected in series and parallel, right? And the voltage can go easily up to 1000 volt DC, okay, or even higher in some cases. So so this and the power level can be of the order of megawatt. Okay, definitely of the order of power, megawatt of power getting exchanged. So this grid here is typically medium voltage grid. Generally this is a medium voltage grid. Okay, because the amount of power that we are exchanging and the voltage levels we are talking about, all these together will lead us to like a megawatt level of power and medium voltage connection. Okay, and just to give you some idea, like lithium ion batteries are the most popular. Okay, and but they also, other types include lead acid battery. Lead acid batteries are wet batteries. Okay, and they are very cheap, and usually we find them very economical also. And but there are other technologies, flow batteries, sodium ion batteries. So you can search in the internet, and this is a huge field of research, particularly in the area of chemistry, where a lot of technologies have been already established, and many of them are upcoming on the different types of chemistries which are used for production of batteries. So but we will not go into that in this course. Okay, so yeah, so the DC voltage is converted to AC and fed to the grid, and the transformer is used for connection to grid, and as well as like filtering and stepping up and down the voltages. Okay, right. Now there are several types of topologies. Okay, we will see some of these topologies here. One is the one which we have just now mentioned, okay, which can be directly connected to the DC-AC converter. In some cases, okay, we also have an intermediate DC-DC stage. Okay, intermediate DC-DC stage is used, right? And this actually serves many purposes. Okay, it can give a more control over the DC voltage. Okay, this voltage, because remember, when we charge the battery, we have two modes of charging, CC and CV mode of charging. Okay, so this mode what is CC mode of charging the battery? CC means constant current. We charge the battery with a constant current, and we take the state of charge SOC of the battery like up to 90%, after which we shift to constant voltage mode. Okay, and a DC-DC converter can do this very effectively. Okay, so it can charge the battery in both CC and CV mode, right? So we sometimes use these DC-DC converters along with the AC-DC converter, right? Now this topology can be also transformerless. When we say transformerless, this is the low frequency transformerless. Okay, but then the isolation will be included in the DC-DC stage. Okay, so we can remove this isolation from here and put this isolation inside this one. So there will be an isolation here, but this will be high frequency, and therefore we will remove we will reduce the size of the converter. Okay, this is the low frequency, this is the 50 Hertz transformer. We can remove this and put it in the high frequency. We have seen one of these very recently in one of the previous weeks that we can use a dual active bridge. For example, this is one possibility of using this DC-DC converter. Okay, dual active bridge. AC-DC flyback converter can also be used, but this is only unidirectional. Okay, it cannot be used bidirectional way. Okay, so at DAB is one of the very promising converter for such battery energy storage system. It can give you a high frequency isolation between the two input and output stages. Okay. Yeah. Now, when we talk about these battery packs, okay, there are two ways by which we can actually connect these battery packs. Okay. Now, one of them, as I am showing here, is this called the series connection. Okay. So here you see that there are several battery packs. Okay, so you see here there is a battery pack, and I mean there are several battery packs here which are connected in series. Now you see here one of the things, this is the plus and minus of the DC-DC stage, and they are now connected in series. Okay, this is where the series connection happens, right? So why do we think about this one? You can see here that these battery packs, as you can understand, these battery packs are generally low voltage. Okay, low voltage. Suppose you can have a battery pack of 72 volt. Okay, you can have a battery pack of 72 volt. Now you can have several such 72 volt battery packs which you connect in series and can reach up to a certain voltage, which is useful for this grid. For example, you have a 400 volt grid. 400 volt AC grid. Okay, you can connect them. Even not 400, even if you say you can have a 3.3 kV AC grid. Okay, even higher than that. It can go even higher than this. So you can think that this grid can be a medium voltage grid. Okay, so this is possible. But now on the low voltage side, you have a 72 volt battery system. So we need some form of a connection on the low voltage side by which we get to a adequate voltage. Of course, you can always say that there is a transformer which is n:1. The turns ratio of the transformer takes care of it, but you cannot have a very arbitrarily large value of turns ratio of the transformer. Okay, so we will need this kind of a series connection of the batteries. Okay, so here the DC voltage is divided among the battery packs while the current remains the same, because the series connection, so the current will remain the same, which is flowing through all the DC-DC converters. Okay, and so lower voltages can be obtained from each battery pack. So from the low voltage we can interface to the medium voltage grid. So this is one type of connection. The other type of connection is possible is this is called the parallel connection. Okay, in this parallel connection, what happens is the voltage here, this voltage remains the same. Okay, but now the currents from all the units get added up, so high current will flow here. Okay, so the current, so lower current rating devices can be used in the battery pack as well as in the DC-DC converter, but then the current gets boosted up, and which one can be fed in the grid. One more advantage is that in case of failure of one battery pack, you can actually disconnect this battery pack, and the remaining battery packs here will continue to operate, okay, from other parallel packs. So this parallel connection is something which is also quite popular. So basically we will just little bit digress a little bit here, and we can show you something which is in general used not only in battery packs but in also other applications like PV systems and all. Okay, and this discussion on this slide is a generic discussion which is not only true for battery systems but also for other systems. and what is this discussion is the what we know, what we call as series and parallel connection of converters. Okay, so this is series and parallel connection of, you can say, converters, or you can say of energy sources, like that. Okay, and so what is this concept? I just want to introduce this concept to you. There is something called as there is some way by which we can connect the converters. See here, for example, let us take this example. Here is this converter 1 and converter 2. Okay, now here you see this is the series input and there is a parallel output. You can see here this input and this input goes and the current gets added up. Okay, and so you can have the grid here, so the grid can be connected here, or you can have a load here. So now what happens here is that this is series input and this is the parallel output. Okay, so this connection is called input series output parallel, or ISOP connection. Okay, input series output parallel connection. Similarly, you can see you can have a parallel input and series output, which is called input parallel output series connection. You can see here the input, this is getting paralleled here, and then the output is series connected output. So this is plus and minus from each of these ones, and then they get added up. Okay, so if you see this ISOP connection, where do we use this one? We use this when we have a high input voltage and we need a high output current. Okay, so for example, this series input can be a grid here. Okay, okay, so let us remove this part. Okay, we can remove this. So parallel output, so we'll connect the battery, so but the battery will be connected here. Okay, so what is done here, this series input, okay, this series input can be a 35 kV source. Okay, 35 kV 3-phase source, so 35 kV divided by √3. Okay, it's a single phase representation of the thing, and this can be connected here. Now what are these converters doing, converter 1 and converter 2? So there can be n number of converters like this. Okay, what is happening here is that all the outputs of these converters are getting series connected. You see here it is all getting series connected, and the output voltage of this converter, of course there will be an inductor in between. Okay, there is an inductor here. Okay, the output voltages are all getting added up. Okay, so that is why we are saying input series. Okay, input series output parallel. Now at the output side, what is happening, all the currents are getting added up and they are being given to the low voltage battery. Okay, so there is a low voltage battery here. Okay, so this converter can be, for example, a DAB. Okay, a DAB along with a DC to AC stage at some point. Okay, so this is the input series output parallel connection. But now you can reverse the input and output side, and you can have a parallel input. Okay, and then a series output. Okay, that series output is the it can be the grid here. Okay, so of course you have a high input current and a high output voltage, right? So this is the IPOS connection. It's the same thing but changing the input and output, right? So then the converters are connected. Of course you can have other types of connections, like these are not popular. Input series output series, and then input parallel output parallel. Okay, these are not so popular, but these connections, ISOP connection and IPOS connection, these two connections you will see being used repeatedly in several battery energy storage system topologies, circuit topologies. Okay, depending on which side is input and which side is output, you can actually connect the input and output in series or parallel connections, right? So this is one thing which we wanted to mention here. Okay, so for example, in this pattern, the input is all parallel connected. Okay, so this you can see here in this diagram, the inputs are all parallel connected, right? uh, okay, now having given a brief idea about the battery storage system, let us also see what are the different utilities or what are the services which are provided by battery storage systems, right? So for example, if you see here, there is this battery pack, right? And we have connected some converters here and connected to the transformer and connected to the transmission line, right? Now many times, okay, many times these battery packs are integrated along with the renewable energy sources. Okay, many times there are several reasons for this. One of the reasons is, of course, as we have said, that renewable energy sources are intermittent in nature. So sometimes the production is less, so we will use the battery to support the grid, but sometimes the production may be more, and so we will store that excess production from the PV panels or the wind farms into the battery pack. Okay, but there are, apart from this, there are many other functionalities of this kind of a battery pack. What are these functionalities? One is called as peak shaving. Okay, so these are some of the services provided by BS. What is peak shaving? Peak shaving means that during peak demand from the grid, okay, so suppose there are certain times of the day, okay, say for example between 6 to 8 p.m, okay, there is a substantial demand from the grid for power, okay, and at that point we can actually, the battery, one of the important characteristics of battery energy storage system is that it can be quickly turned on and turned off, unlike gas turbines. Gas turbines take a lot of time to start its full production capacity. Battery storage systems can be quickly turned on. So if the grid demand is quickly changing or it's quick going up, we can immediately connect the battery system so that the peak, during the peak power demand, the consumption, so we can supply to the grid. Okay, so typically something like this, if you see like this is the power consumed with respect to time, and this can be like 6 to 8 p.m. okay, and normally the synchronous generators will be able to say supply this one. So this is the alternators, and this area, okay, can be easily supplied by the BESS, okay, the energy. So this is the peak shaving. Okay, you can get that peak part of the power, okay, from the battery. But then when the demand is going down, suppose we are coming here, okay, when the demand has gone down, then you can again charge up the battery here, and this can be done when the cost of the electricity is low. Okay, here the cost of the electricity will be high. Usually the cost of the electricity is very high during this point, but here the cost of the electricity will be low, right? So this is one service which can be given by the battery storage. Of course, we have seen this one, we have talked about it, support for the renewable energy plants, okay, to help maintain stable power levels. The other one is spinning reserve. What is spinning reserve is, it's providing a fast response backup power. Okay, so if there is a sudden load surge, Okay, so sudden load surge. For example, there is one plant or something, a big load region which has a sudden surge in the load. So it is drawing suddenly without any notification. Suddenly there is a load surge. As I told you, BESS systems have a very fast response time, much faster than traditional synchronous machine based system, and so the battery energy storage systems can actually cater to these sudden load surges because their time constants are much faster. It can quickly turn on. Okay. The other point is the frequency support. What is frequency support? Frequency support is, now since this is something which is happening very frequently nowadays, and what we are seeing even in India, as the renewable energy penetration is increasing, what we are seeing is the grid is sometimes getting disturbed. In particular, the frequency of the grid is getting disturbed often. Why the frequency changes? If you remember, the frequency is dependent on the alternator's mechanical motion. It is related to frequency. So that creates the frequency of the system. Now what is happening is the renewable energy production and the nature of renewable energy is intermittent, and it can fluctuate widely, okay, very quickly and widely. So what it is happening is that the overall frequency regulation is getting affected, okay, because of the because of the intermittent nature of the renewable energy. The frequency of the grid is fluctuating a lot, okay. The change in the speed of the alternator, and so there are different time constants involved in the whole process, but there are wide fluctuations in the frequency observed, okay. Also remember that as more and more renewable energy is integrating, of course we will go on reducing the number of alternators in the system. The alternators have a huge mechanical inertia that gives the stability to the frequency, because it is not easy, or it is not easy to kind of like change the rotation of such a big machine. That gives the frequency stability, okay. But if in a grid, say 50%, 60% is renewable energy, 40% is alternator, so the total inertia in the system is much less compared to what we have today. So what is happening is the frequency is very widely fluctuating because of this lower inertia of the whole system. So therefore during these kind of frequency oscillations, right, the BESS can support the microgrids to operate independently, okay, by providing frequency regulation. This is especially true for microgrids, okay. Microgrids are small grids which are weak in nature, and they have a lot of fluctuations in the grid, in the frequency. So here BESS is kind of like almost essential to have a part in the microgrid. Black start capability. So if there is a full blackout in the grid, so BESS can actually start the grid or grid restoration after the blackout because of its inherent energy storage, okay. And of course you can also have a power quality improvement, okay. So the BESS can act, of course, like a STATCOM, okay. It can provide active and reactive power support, okay, both the active and reactive. So of course we were talking mostly of active power so far, but a battery energy storage system can also provide reactive power to the grid as and when required, okay. So therefore it can act as a STATCOM, giving both P and Q to the grid support, P and Q support, okay. So this is possible. Also you can work the BESS to work as an active filter, okay. It is possible to do it, although generally not done much, but you can help it to improve the power quality, okay. So these are some of the services which can be provided by the BESS system. Now looking into a little bit more into the different converter topologies. We have seen some of these isolated and non-isolated topologies, but especially for higher voltage. Now we also said that there are ISOP topologies and IPOS topologies, right? Series connection of input when we have a large input voltages like that. So multi-level converters is also another type of converter which are used for BESS systems, which very much frequently used. Okay, we have seen such one topology, NPC rectifier, but we will just briefly introduce you to these two topologies, CHB and MMC. They are modular in structures, and the cascaded edge bridge and modular multi-level converter. These are the two other topologies. I'll briefly introduce you here because they are very suited for battery energy storage systems. So what are these ones? So you can see here the CHB, cascaded edge bridge, is a like this. Okay, so this is called the sub module. This SM is called the sub module. This SM is called the sub module, and usually you have a battery storage system like this. Okay, for all the, so this is like A phase, and this is connected to the grid. Okay, okay, so here also you can yeah, so so here is this star connected connection. It is, and here, so these are the sub modules here. Okay, these are the sub modules, right? And you can see these are all series connected. They are series connected here. Okay, and this series connection you can also do it in a delta connection. So this is the delta connection here. Okay, so these are the sub modules, and you can have it in delta connected, but then you have the grid here. Okay, so this is what is called as a cascaded edge bridge. In the delta connection also you have the batteries here, right? All the phases will have n number of sub modules, and in all of them can be connected in like this fashion, right? Now what is there inside this sub module? Typically inside the sub module we have actually a full bridge, something like this. Okay, so these are the two outputs, say A and B, and these are the two outputs A and B here. Okay, and the battery is connected here. So H bridge is used in these, inside these sub modules. Okay, yeah, so this is what is an H bridge having isolated DC as the battery. So this is the connection here. Okay, so what happens here is that basically you have like a voltage, as we have seen here. You can generate a quasi square wave from each output having we have seen this quasi square wave in the dual active bridge, right? So this output here, we have seen that it can be a square wave or a quasi square wave like this. We have seen this. So when we talk about multi-level converters, we talk about the levels of voltages. Okay, so then you have this 0, then you have plus VDC and minus VDC. Okay, so these are the voltages which are possible, right? If VDC is the voltage here, then the way you turn on and turn off the diagonal switches, you can get this kind of voltages here. And so each cell generates 3 voltage levels, 0, VDC and minus VDC, and by stacking multiple H bridges in series, so the converter can synthesize a stepped multi-level output waveform. And so here you can see how we create this one. So suppose you have this voltage VDC here, okay, and this is producing the output from this is this quasi square wave. Okay, the output from this is another quasi square wave, but the width you can see this width is different from this width here, which is again different from the width here, right? So basically you are changing the width or changing the output voltage pattern of each of these cells or each of these submodules, and thereby the total output voltage can be something like this voltage, okay, where you can see the sine wave is part of it's embedded inside here, okay. So this is how a CHB or cascaded edge bridge works, okay. The output voltage is the sum of voltages from individual cells, and so VAN is V1 plus V2 VN, like this. So basically the first cell has a voltage like this, okay, and the second cell, the fundamental, so this is the fundamental output inside, and the second cell can have this as the fundamental output, which is different, and the third cell can have a different fundamental output here, okay. So you go on adding this plus it, and together we'll get the large fundamental, okay. So this is what is the basic idea, okay, and this is like the fundamental component inside this waveform here, okay. So we approach the desired sine wave. So we this is one of the very suitable topologies, because now here we have this is the low voltage side, right, and this is the high voltage side which comes across this in. So in this in we get the high voltage, okay. So from the low voltage we can get easily the high voltage. Of course we will have probably a transformer isolation somewhere here, okay, so as to connect it to the grid. We need the isolation, otherwise we have to provide isolation inside this, otherwise this submodule should have a DAB, okay. So the DAB should be present here so as to create the isolation, okay. Any approach is good. So you can see these videos here, okay, you can see these videos because we have another course which is exclusively for these multi-level converters. You can have a look into those courses, okay. There is also one important converter which is also called the modular multi-level converter. We want to introduce you here. It is very similar to CHB in its modular structure. What happens is here, so the battery cells, so here also you have these submodules, right, and the submodules have this battery storage system. So but now the connection is a little bit different. How is the connection? You can see there are these there are 6 arms, and there is a upper arm and there is a lower arm, right, and so here what happens is these submodules, there are total 6 arms, and the submodule, so this is like A phase, this is A phase, and this is B phase, and this is C phase, okay, like this. The grid is connected here, so this grid is connected like this: A phase, B phase, and C phase, right? You can have an isolation here also, right? You can have a 3-phase transformer, or rather I should draw it like this way. Okay, 3-phase connection here, right? Now, so what happens here? It is very similar to the cascaded edge bridge, because here also you have these small voltages coming here, and these voltages will get added up and will create the large voltage here. Okay, so they basically, this will act as a controllable voltage source, and so now, but we have 6 controllable voltage sources. Okay, consists of an upper arm and lower arm. Okay, and each arm consists of full bridge or half bridge submodules. So inside these submodules, we can actually, this is the advantage of having this structure, is that we can actually have a half bridge submodule also, unlike CHB. In CHB, we will have definitely a full bridge, which we also seen in the last slide. But in case of MMC, we can actually have a half bridge submodule. Okay, and that actually helps a lot because it reduces the semiconductor losses, right? uh, Now these submodules, like the CHB, we will insert or bypass these submodules, right, from the arm. So for example, here I am showing with the half bridge cell. So you can have like this, here you can have either a 0 or VD voltage. Similarly, this one also can have a 0 and VD voltage, and by adding all these modules, so you can have like a stepped waveform, which is shown here. Okay, so one cell is producing this voltage, the other cell is producing this voltage, the other cell is producing this, like this, right? This is how the stepped voltage is made from these cells. And so the fundamental component inside this voltage is something like this. Okay, you can make it by adjusting the pulse width modulations. Okay, of course, when you have the full bridge, it is even easier. So in this half bridge case, there is a DC component. Okay, so there is a DC created. But in case of a full bridge, what happens is, when you add these steps, okay, and you manipulate, then you get this voltage, which is here. This is the AC voltage which is you are creating. Okay, so these are the full bridge cells which we use. Okay, so with many cells, the output becomes very smooth. So this is the one of the advantage of this converter. Like you can have hundreds of cells, and so this output here will become like almost close to a sine wave if you see the actual output waveforms. But the advantage here is this voltage here, which is coming from the battery here, this can be very low voltage batteries, low voltage battery, but high voltage on this side. Okay, because you have hundreds of such cells, right? So this is some of the features, which is again, so we have the modular identical cells, which is very important because all devices, all semiconductors, everything are identical, batteries can be identical, etc. Each arm can contain more than hundreds of cells. So low voltage batteries can be connected to each cell so that we get to a high voltage, right? So low voltage semiconductor IGBTs can be used. Fault tolerant operation is possible. What we have not talked here is there can be a bypass feature for each of these cells. So if one battery pack is bad and you want to remove that battery pack, you can bypass that cell, okay, by this bypass switch here. This is the bypass switch, okay, which we have not shown in the circuit diagram. And easy scalability of voltage and current. Why easy scalability? Because you can design for say 100 cell, and in the next application you can design for say 125 cells, 130 cells. So you can basically increase the, or you can decrease, instead of 100 you can decrease to 70 or 60 cells in the arm. And the reason is that it is easy to scale because it's identical. Okay, so scalability of the voltage and current and power is possible with this kind of converter. And the converter is bidirectional in nature. So as I told you, if there is a grid here, okay, the power can actually flow both ways from the converter to the grid, okay, both ways. So it is, by nature, it is a bidirectional converter. Okay, now there is some special feature. So for a detailed study of MMC, you can refer to these slides, which are again available, right, in the YouTube. Okay, but one of the things is in MMC there is a unique feature which is called the circulating current. Okay, so by proper manipulation of these voltage sources, so we have a voltage source here and we have actually a voltage source here. In fact, we have 6 such voltage sources and we can manipulate these voltage sources here. Okay. Now, by manipulating these voltage sources, what we can do is that we can allow this kind of a circulating current to flow inside the converter. Okay, we can allow this current to flow. Why this is a circulating current? Because this current does not flow from the DC or the AC side, but it keeps circulating within the phases. Okay, right. So there is some current which will continuously flow inside the phases, and what happens is, because this circulating current is flowing, you can actually, with the help of the circulating current, you can adjust the state of charge or balance the state of charge of the batteries. SOC of the battery is an important parameter which must be maintained for all the batteries. Okay, the state of the charge of all the batteries should be ideally at the same level all the time. Otherwise, one battery will discharge more than the other battery. So, with the help of this circulating current, it is possible to actually balance the SOC of the batteries. Okay, again, I will refer to you to this slides or the lectures where we will see how this can be done. There are also very interesting possibilities with these kind of converters. We'll just show you one of them, is that the PV and battery systems can be integrated inside the converter. Okay, inside the MMC. Okay, for example, you can see here there is a one MMC, and here there are PV cells. Okay, here there are PV cells and an isolated DC-DC converter which is connected to the half bridge. Okay, and this is in the upper arm, but in the lower arm you see battery storage system. Okay, so one arm itself, okay, in one phase you can have a battery and a PV integrated together. Now what happens here is that this current, so the energy will always flow from the PV to the grid or to the other phase, but the energy from the battery is bidirectional. So the power here and the power from the PV is only unidirectional, but power from the battery is bidirectional. Okay, so what happens now is that we can actually, from this, say, battery power, it can flow this way and some part into the grid. Okay, right? Or if you want to charge the battery, then you can do something like this. It's offer. So from the PV you can charge the battery like this, and something from the grid. Okay, so you see the amount of flexibility that you get. Okay, so inside a single converter you have all the features, and you can charge, discharge the battery, you can integrate PVs, all of them at low voltages, and you are connecting to the medium voltage grid here. Okay, medium voltage or high voltage grids you can connect to there, right? Using low voltage battery packs or low voltage PV systems like this, and power can be seamlessly flow. We have papers on this, but so power can actually seamlessly flow from upper arm to lower arm and like that. Okay, to the other. So this is what we have. Okay. Now the control strategy for battery storage system, the main objectives of this controller. Okay, so it is very simple, and we already know this one because we have studied this as part of week 4, 5, 6 like that in one of this module B. So you should look into module B. Okay, module B covers all this in very details. But just to recap what we have done, it regulates the active power, okay, for charging and discharging. Basically, when we connect the battery storage system, then we are charging or discharging the battery, and so we need to give a P reference, okay, P start. We have to give a P start to the converter to charge or discharge, okay, and we can also have the reactive power support for the voltage. Okay, we can do this one, right? Yeah, so we can actually provide the BSS, but it is much more than that. Actually, you can have P, you can have reactive power, you can use that P to provide virtual inertia. You can use that P to give frequency support. So many things are possible from the BESS point of view. So all those features which we had discussed, right? Peak shaving, and then frequency support, virtual inertia, power quality, STATCOM operation, all these things are done with the help of tweaking the controller. Okay, and we have studied it in details in module B, okay, where we have seen how a voltage source converter can be given one P star and Q star commands, and the voltage source converter can deliver that. So the controller for two level converter, it remains the same. Okay, so DQ control, we basically use the grid voltage oriented vector control. Okay, so if we want to charge the battery, we can also have a CC mode of charging. We'll talk about it sometime later. Okay, but when we talk about these multi-level converters, just make sure that the control strategy is very similar, but some additional requirements are present, like voltage balancing among the various phases, arms and some modules, and the circulating current control. And these are shown with these block diagrams, because in multi-level converters we have several small modules and we have to kind of like control them. Some module energy balancing, overall state of the charge control, then circulating current control. You can refer to some of the papers, recent papers, in which all these factors have been taken care inside one control block, and is given this one to the finally to the PWM module, and that will give the pulses to all the cells. So here are some of the example ratings, some of the ratings which we have seen. For example, this you can search in the internet. A lot of literature is available. We have taken this data from this literature. Okay, here we are talking about some of the energy storage. So just to give you an idea of how much is the power rating, for example 2.8 megawatt or 20 megawatt here for the Mira Loma substation, and so the total energy capacity, okay, this is a smaller one, okay, but you can see the larger one is 80 megawatt hour. Okay, and so and their key purpose is like manage reverse power flow from the solar, so it supports the solar PV panel. And also, but this one, the Mira Loma, it can store off peak energy, right? So it will store that high energy, supply peak demand, so which is helpful for peak shaving, and then increasing the grid reliability by providing the active power when as and when required. Okay, so there are several functionalities, and some of them we have seen in the previous slides. You can search in the internet, you will get a lot of articles, because this is an area which is a very much growing area, because we have seen now that the renewable energy, we have adopted renewable energy in a big way, and in the future also the percentage of renewable energy in our total energy consumption will be very high. But renewable energy has certain very important challenges which must be solved, and the easiest way to solve, there are several technological solutions, but the easiest way to solve is through this battery energy storage system. Now we come to one last subtopic here, which I want to spend some time. One of the things that we have said is that the battery storage system can support the grid. Okay, now there is something called as so when we actually so this is when we actually say that we are supporting the grid, there are two ways to actually support the grid. One way is to inject a current to the grid. Okay, so here is the grid. One way is to inject a current into the grid. Okay, so this is how we have actually always studied the voltage source converter, because remember, okay, if you remember the voltage source converter, so the voltage source converter was connected to the grid, and what we have given to the voltage source converter, P star and Q star, which if you assume that the grid voltage is constant, this P star and Q star basically means that we have given ID star and IQ star, okay, to the voltage source converter. What does this mean? It means that basically we are injecting a certain I grid into the grid. We are injecting this current into the grid, okay, always, irrespective of what is the grid voltage. So the grid voltage here can fluctuate, but whatever may be the case, I am going to inject, because the voltage source converter is acting like a current source. So this is the voltage source converter here. This is the voltage source converter. It is acting like a current source, okay, and therefore because it has this ID star and IQ star, right? Now therefore whatever happens in the grid voltage, no matter if the grid is, suppose there is a grid voltage sag, there is a grid voltage swell, we have seen in the simulation also that even if there is a perturbation in the grid, we are going to inject a certain current into the grid no matter what happens. So this kind of control is called the grid following converter, because it precisely follows the grid. And this is true when the grid is strong grid, because in a strong grid the PLL, okay, the phase lock loop, accurately maintains, so the grid voltage does not fluctuate too much, the frequency does not fluctuate too much, and the PLL is nicely synchronized with the grid voltage. So following that PLL, we inject the current. Because the PLL is very important. So if you see the vector control, we have to align the grid voltage space vector, right, with the theta. That theta angle, that is the PLL's angle, that angle is nicely aligned with the grid voltage space vector. And so we follow the grid basically, and we are going to inject the current ID star and IQ star based on that theta angle. However, this is not always true, okay. So there is another possibility which now comes up, okay. So this is the grid forming converter, okay. So it is a power electronic converter that can create and regulate grid voltage and frequency like a virtual synchronous generator or virtual synchronous machine or an alternator. What it is doing then, again the same VSC, it is the same VSC, voltage source converter, but it has a different reference. Now we are asking the voltage source converter, so this is where the voltage source converter is. So now we are asking the voltage source converter that, well, you make a constant voltage. So it is what is making. It is going to make a voltage at a certain angle, okay, with the grid, okay, and this angle is usually 50 hertz, okay. So it is going to create a voltage at a certain angle. So this will be the reference for this converter, and this is called the grid forming converter. Why it is grid forming? It is grid forming because the voltage source converter is behaving like a voltage source having its own amplitude, frequency, angle, okay. So it is acting as if like a new synchronous machine, controllable synchronous machine added to the grid, okay. The grid has several synchronous machines. Remember, the grid is made up of several synchronous machines plus renewable. Now if the percentage of the renewable is high, what happens is, if this percentage of this renewable is going up and up, then synchronous machine percentage is going down, right? So what happens is that the grid will start to behave as a weak grid, or sometimes in case of also a microgrid also. So then the voltage, then the frequency will start to vary a lot. Okay, and there this grid forming converter starts to play a very important role, because it acts as a controllable synchronous machine inside the grid. And who gives it the active power? Of course, then we have the, here we have the battery, BESS. BESS is the energy source to this voltage source converter. So a BESS based voltage source converter can act as a grid forming converter. Okay, so it sets and maintains voltage and frequency references, can provide inertia and frequency support. What is inertia support? Inertia support means when the frequency is falling, it actually falls to some nadir and then it starts to go up. So it typically the frequency is something like this, okay, frequency with time, and it tries to come back to the nominal frequency. Okay, so during this, when the frequency is going down, then you have to inject a certain amount of active power. Okay, and that is like a virtual inertia. Why it is a virtual inertia? Because the inertia of the synchronous machine is in the mass of the synchronous machine. It's a big machine. It has a half j omega square. So rotational inertia is there. So a lot of energy is there. That energy is now replicated by the BESS. So the BESS is providing that energy. There is no physical synchronous machine, but the energy from the battery, we can inject it in such a way, in a controlled fashion, so as to mimic the behavior of the synchronous machine. Okay, so this is therefore the BESS based grid forming converter. So it can be operated as a standalone power system. So you can, renewable based weak power systems can operate stably. So this is one of the very important application of BESS systems which we see in the near future. So now we are going to talk a little bit for about say 15-20 minutes about the battery management system, and we have seen the different types of battery energy storage system and the power converters which are used for this BESS. But now we will briefly talk about the battery management system. It's basically, if you see, a battery management system is an essential component for the battery energy storage system, because it manages the whole energy flow. Okay, and not only that, it's not only does a charge discharge of the battery, but it also controls the health. It is responsible for the safety of the safety and the performance of the battery modules. Okay, so it monitors the operating conditions, for example the temperature, and protects against faults to ensure a long battery life and safety and longevity. Okay, so these are some of the things which a battery BMS system does in a battery storage system. And in fact, for it is so much essential that there are dedicated ICs available. There are a large number of dedicated ICs available for BMS system. For example, we have given one from one manufacturer, but there are several manufacturers who are actually having dedicated ICs for the battery management system. Okay. Now, what are the typical functionalities of this battery management system? Is that of course it does the monitoring of the battery. Monitoring means the state of charge and state of health of the battery. Okay, we'll talk about this thing. Number two, it does the protection. Okay, so it protects in case of suppose a short circuit or fault, something like that. Then of course it controls the charge and discharge. So a battery can be charged or discharged at different C rate. Okay, C rate means is the charging rate or the discharging rate of the battery. So the current that flows into the battery, the current can be controlled. You can charge a battery at higher current or lower current, but it will affect the lifetime of the battery. So this charging and discharging, the how or at what current we will charge or discharge the battery is very important. And so this is also part of the BMS. And then we have the communication. Okay, the BMS ICs generally have a communication interface. For example, the IC which I was talking about, it has a dedicated communication channel by which you can send the status of the battery to the end user. It has limited diagnosis capacity also. And one more important thing is many of these ICs have cell balancing feature. Cell balancing means a battery is never a single battery. There are multiple low voltage batteries, suppose 4 volt or 3.6 volt batteries, which are very common. So these kind of batteries are stacked in series and parallel combination. So we have a stack of batteries. Okay, what happens is that all the batteries, all the cells inside one stack, they are not at the same level of voltage and at the same level of voltage. So what happens is when you start delivering current or extract current from this cell, some of the cells will discharge more than the other cells, and this process will go on continuing in such a way that you may find quickly that some cells have completely discharged, okay, while other cells are or other stacks are not fully discharged. Therefore, and this will cause the overall voltage to fall down. Okay, so therefore what happens is there is something called as a cell balancing, okay, in which you can basically balance the output of the cells, and you can divert some current from one cell to the other so that all of them have their same state of the charge at any point of time, ideally. Okay, we try to achieve that one. So cell balancing is also a very important feature. The BMS does this one either through some dedicated circuits, through some additional transistor based circuits, or some passive resistors. Okay, so this is also the functionality of the BMS. Yeah, so this is what I was talking about. What are the monitoring things? So it monitors the pack voltage, cell voltage, current, temperature. Also it can detect this over voltage, overcharge conditions. Okay, and temperature monitoring is also important because otherwise it will lead to overheating. So temperature controls the rate of reaction inside the cells, and that is also important. And isolation monitoring, because many of these, suppose in a car, this battery pack or battery bank, whatever you say, this has quite a high voltage. It can easily go to 800 volt or 1200 volt, and so isolation monitoring is very important in this kind of battery system. Okay, now apart from the monitoring part, BMS can also estimate, okay, certain parameters of the battery. Okay, what are these parameters? These are the state of the charge, state of health, depth of discharge, or internal temperature. Temperature is very easy to understand. You have a temperature sensor through which you can estimate the. But what are these terms? SOC, SOH, DOD. So let me explain this one. What is SOC? SOC means how much charge remains in a battery expressed as a percentage of the full capacity. Okay, so SOC, for example, so mathematically, remaining capacity at a time t divided by the maximum available capacity. Okay, so you have seen even in your mobile phone charger, you can see at any point of time there is an indicator which shows that how much is the charge left in the battery. Okay, so you typically have this kind of a symbol, and you can see that, okay, this is like this, and it says that 60%. So 60% here means the SOC of the battery, how much is available. Okay, so remaining capacity, so this is the remaining capacity divided by the maximum available capacity. So a capacity usually of a battery is denoted in ampere hour or milliampere hour. Okay, it's basically the unit is coulomb. Okay, one form of coulomb. Okay, so ampere hour, so the or ampere second, so coulomb is nothing but ampere second. So but we use a different type of unit, but the basic idea is current into time. So there are various methods by which SOC can be estimated. So you can estimate the SOC, and there are Coulomb counting method, open circuit weld method, or Kalman filtering method. We are not going to talk in details about this, but what we are going to so you can search in the net about these methods. We are not going to go much into depth. Only we want to just briefly touch upon the Coulomb counting method. See, basically what it does is that the SOC, okay, at any time t is the initial SOC. This is the SOC is the initial SOC. Okay, SOC represents the initial SOC. Okay, and times how much is the charge. Okay, this is the charge which is going down. Okay, which is going outside. This is the charge which is lost or which is injected into the battery. Okay, so this is the charge. So I bat is the charging current. Okay, and this is how much you are losing or getting. Okay, losing or gaining, right, divided by the Q rated. Okay, as percentage of the Q rated. Of course you have an efficiency, because charging or discharging does not take place at 100% efficiency. So this is how the state of the charge at any instant of time t can be obtained, provided you know accurately what is the initial SOC. Okay, this is the problematic part in the Coulomb charging counting method. Getting to this initial SOC is a little bit tricky. So okay, but once you get that initial SOC, then you can find out, okay, how much charge has been taken away from this battery, and then what is the remaining SOC. Okay, pretty simple. The other point here is the state of health, SOH. Okay, now state of health is also very important from the battery point of view. It is the current condition or ability to store and deliver electrical energy compared to its original new state. Okay, SOH is the present maximum capacity divided by the new rated capacity. So what does this mean? It means something like this. So suppose you have a battery here. Okay, and if it is a new battery, okay, if it is a new battery, then suppose this box here represents the charge that you can store in the battery. So in a new battery you can store, say, 100%. Okay, let us take 100%. Now suppose you take an old battery. Suppose you take the old battery. This is one old battery. Okay, and in an old battery, because of the chemical reaction and the aging, okay, what you will see is that, see, you can only charge Q equal to 70%. Say it's an old battery, 70% of the max of the original new rated capacity. Okay, so here what happens is, even if you charge the battery, even if you make your SOC 100%, it can only charge up to this capacity. This is important to know. So this will be the maximum you can charge now. Maximum one can charge. Okay, so whatever you do, you will not be able to get the perform or the total charge which you can store in the red colored battery, the new one. Okay, so if an old battery comes, then you will be only able to store 70% or 80% of the original capacity. That will denote the 100% SOC. Okay, that corresponds to, even if you charge with like, and your indicator shows it is 100% SOC, actually you are charging, as compared to the new battery, you are charging only 70% or 80%. Okay, so this is also an important parameter to note, and the BMS actually can find out what is the state of health of a battery. Generally SOC less than 70%. In many applications it is considered that the battery has aged a lot. Okay, so we have to discard the battery. Remember that with SOC, with SOH, what happens is you will charge and discharge your battery much quicker. So the problem is that you will discharge the battery very quickly if it's an old battery. In a new battery you will be discharging at a slower rate, but in an old battery you will discharge it very quickly, so the battery becomes unreliable for many applications. So that is all the reason why we put it less than 70% as something which is not considered good. Okay, what is depth of discharge? Again, another terminology. It is just the complement of the state of charge. Okay, it is 1 minus or SOC, like 100% minus SOC. So it means how much we have drained the battery. So if the battery is fully discharged, then if it is fully charged, then SOC is 100% and depth of discharge is 0%. And if the battery is fully discharged, so if it is fully discharged, then SOC is 0% and DOD is equal to 100%. Okay, generally we don't go up to 100%. Generally like close to 15 to 10% of the SOC, we say that we have to charge the battery once more. Okay, there are different types of batteries. Okay, lead acid battery is very cheap. Okay, but it is a wet battery, so there is a chemical reaction that happens. Okay, acid is there and a chemical reaction happens, and used in inverters. Many of you have home inverters, and there you will see that lead acid batteries are many times used. But lithium ion batteries are dry type, and it is very popular for electric vehicles. Okay, it is the most popular choice now, lithium ion batteries. Nickel cadmium, mostly used in low voltage electronics. Okay, you will see battery cells there, we will have the nickel cadmium. Okay, now BMS has some feature for battery protection. Okay, it protects this one. So different types of protections are possible. Electrical, thermal protection. Of course, thermal protection is done by temperature sensors, but electrical protections, you can have current or voltage protection. Why they are important? Because voltage protections, okay, so the lithium ion cells, for example, must operate within a safe voltage range. Okay, so these limits are important because otherwise if you do not if you cross these limits repeatedly, then you are going to degrade your battery life. Okay, so what the BMS does is it will stop the charging as the voltage nears the upper limit, or it will limit the discharge when it is reaching the lower limit. Okay, similarly you have a current protection also. Okay, BMS limits the keep the battery within the safe operating area defined by the manufacturer. So here you can see, suppose this is the safe SOA of a lithium battery. This area is the safe operating region of the battery. Now suppose you are charging, okay, you are charging, so the maximum peak charge that you can do is up to this 15 ampere. Okay, similarly when you discharge, the maximum discharging is the -8 ampere. Okay, and in this one okay, the battery voltage will fluctuate between like 2.6 volt to 3.8 volt, like that. Okay, so this is the safe operating area of the battery. Okay, and in this one you can actually charge the battery at any value of current. Okay, similarly you can discharge the battery at different values of the current. Okay, so the battery cell manufacturers typically define the maximum continuous and peak current limits, but there is also a very important factor which is called the C rate of the battery. Okay, what is C rate of the battery? And one must know that when you are dealing with the batteries, you must understand what is the C rate of the battery. Okay, what is C rate? Okay, for example, to understand the C rate, we have to see that suppose we have to see that a battery capacity is the number of ampere hour that the battery can supply after it is fully discharged, okay, or is fully charged. So we have said this one, like so suppose it's like the capacity of fuel in the tank of a car. So suppose you have an 80 ampere hour battery, okay, so it can supply 8 ampere of current for 10 hours before it is fully exhausted, right? Because 8 amperes, 8 into 10 is equal to 80. So 80 ampere hour is what is the when you go and purchase the battery from the market, they will say that it is an 80 ampere hour battery. Okay, so you will be like saying that, okay, I can supply 8 ampere for 10 hours. Now suppose you have an application and you connect your battery to a load, okay, and that load is drawing 16 ampere. Okay, so you have the battery, this is an 80 ampere hour battery, you have put it to a load, but the current which is drawing is now 16 ampere. The resistance of the load is such that it is drawing 16 ampere. Okay, what will happen? You will expect that, okay, I had 10 hours, okay, because the total ampere hour is 80 ampere hour. So if I draw 16 ampere of current, so it will last for 5 hours, right? This is what the mathematics says, but it will not happen. Okay, rather this 5 hour will go down to say 4 hour or 3 hour. Okay, why will it happen is that, so the same battery will not last for 5 hours if you draw 16 ampere of current. Okay, because this 80 ampere hour, the capacity of the battery as 80 ampere hour, that capacity changes when you draw different types of currents or different magnitudes of currents from the battery. Okay, this is where the C rate of the battery comes in. Okay, so C rate is a measure of the rate at which the battery is discharged relative to its maximum capacity. Okay, so a 1 C rate means that the discharge current will discharge the entire battery in 1 hour. Okay, so for example, if you see here, suppose you have a 1 ampere hour battery, okay, so which means that it will, so you will 1 ampere for 1 hour. Okay, so you can draw 1 ampere for 1 hour. Okay, but now suppose you draw 2 ampere from the same battery. Okay, so you expect that the battery should ideally deliver for 30 minutes, because 2 ampere into 0.5 hour is equal to again 1 ampere hour. Okay, but because of the internal losses, now you are drawing more current. Okay, so what will happen is it will have more internal losses, and the chemical reaction inside the battery will happen at a different rate. Okay, for which the resultant capacity of the battery will not be any more 1 ampere hour. It will become say 80%, it may become 80% or 70%, like 80% of 1 hour, 1 ampere hour. Okay, it may become like that, 80% of 1 ampere hour. So which means that if you draw, if you draw 2 ampere, it will only last say 24 minutes instead of 30 minutes. Okay, so you expect that 2 ampere is, so if you therefore increase that 2 ampere to 3 ampere, and you expect that with 3 ampere, because it is 1 ampere hour battery, so you are drawing 3 ampere, you expect that it will last for 20 minutes. However, it will not last for 20 minutes. It may last for less than 10 minutes, although it is rated as 1 ampere hour. So if you draw the current more from the batteries, then it will last much less than what is the total capacity of the battery, and that is why the C rate of the battery is very, very important. Okay, the reverse is also true. Suppose you have a battery and you are drawing the current at 0.5 C rate, okay, or 500 milliampere. then what happens, you are going to increase the capacity to more than 100%. Okay, so the battery may last more than 2 hours. Okay, this can also happen, right? So this is something which is important, and the manufacturers, you can see here one manufacturer, some data we have copied. Okay, so the C rates can vary substantially. Okay, so for example, let us consider this one. This is one battery. Okay, so this is the characteristics of the lead acid battery. Okay, and you see how the terminal voltage with respect to 1C. Okay, so if you draw 1C of current from this lead acid battery, then you will be able to maintain the voltage of say 12 volt, and say suppose my threshold voltage is 11.5. so I will draw a line here that 11.5 volt is the point at which my operation will stop. Okay, so you can go up to this point, right? So which means that if you draw 1C current, then you can actually use this battery for 20 minutes only, right? But on the other hand, suppose you draw 0.05C. okay, you are drawing 5% of the C rate of the battery. Okay, so then what will happen is, you can see you will follow this curve, and you can then see that up to this point, okay, which is like 15 hours, you can use the battery. Okay, the area under this curve indicates the ampere hour. Okay, so which means you can see that if you draw with 0.05C, the ampere hour of the battery is increasing as compared to the green case. Okay, so this is important for you to observe, that if you can reduce the C rate of the battery, then you can actually prolong the time duration, not only by time but also the capacity increases. Okay, of course you also have battery thermal protections, which is very important. Okay, because the battery performance and capacity decreases. So here you can see that so during charging point, okay, there is a region, okay, there is a region of safe operating area, like between 0 to 45 degree, okay, something like this you will operate. On the other hand, during discharge time, you can actually go from say -20 to 60 degree, this whole range. Okay, so what the BMS does is, we have seen this in many intelligent BMS. What they do is, it not only handles this thermal regulation, but in order to charge or discharge the battery optimally, it can use an intelligent heating and cooling of the BMS of the whole battery pack. Okay, so suppose you want to charge the battery, and the current temperature outside, the current temperature is say -30 degree, and you are trying to charge the battery. This is suppose the ambient temperature. Okay, and you are going to charge the battery. So the BMS can actually, through some internal energy sources, can heat up the battery. Okay, heat up the battery to heat the battery from this point to this point. So internal temperature of the battery can go say like this point. Okay, like it can go to 10 degree. You can make the battery pack temperature 10 degree centigrade. After it has reached 10 degree, then you start the charging process of the battery. Okay, so these are intelligent BMS systems. They will internally heat up the battery first, so as to come to the optimum charging temperature, and then start charging when the outside temperature, okay, the outside temperature is outside this permissible limits of the safe operating temperature area. Okay, so there are several battery charging methods, but the most important is this CCCV mode charging. So you can charge the battery with constant current, constant voltage, but generally a combination of CC-CV is done, and multi-stage MCC charging is also done. So what is basically done, you can see here through this curve. What you do here in constant charging is, for a certain, so this is typically used, this is the most common way of charging a battery, right? So what you do here is, this is the constant charging, current charging. So initially you charge the battery at a constant current level, okay, and therefore the battery voltage here will rise, right? After the battery is at a certain value, typically this is like 90% typically, okay, 90% of the rated voltage of the battery, then you shift to constant voltage charging, okay. So the battery voltage at the terminal from the external charging device, the voltage will get fixed, and so then the current will fall, but the voltage will go on increasing slightly until it reaches 100%, okay. So this is the charging start, and when you will finish the charging, right? So this is the CC-CV charging mode, right? There is also MCC charging, so it is multiple charging profile. You use multiple charging profile. You can see, you can have CC1, CC2, like that, okay. So initially you charge with a certain current, then you decrease the current as your voltage or your SOC is increasing, you go on decreasing the current. So this is more advanced technique. So you can actually have a comparison between the different techniques like CC mode and CV mode, but this is the most preferred method, CC-CV mode, because it gives good safety and speed, okay. The other methods have certain disadvantages, and so yeah, okay. And lastly, we will just briefly touch upon the equivalent circuit model of the battery, okay. So typically, as a first approximation, we use a battery, this is the terminal voltage of the battery, and open OCV is the VOCV is the open circuit voltage of the battery, okay, when there is no current flowing, okay. As soon as the current starts to flow, there is a IR drop across this resistance. This resistance value also changes with time, as well as with aging, as well as with the chemical reaction that is happening. So this is the first model that we use. V at the terminal, VT is equal to VOCV minus IR drop, okay. That is the first model. However, there are some other more elaborate models, okay, because as the temperature rises, okay, you can have this temperature effect, so the resistance is changing, and you can have this effect by having an RC time constant in the circuit, okay, several RC time constant, because what will happen is, as the temperature is increasing, the dynamics of the internal resistance is changing, right? So you can model it by this RC circuit, by which the resistance value will go on changing, okay, or the voltage across, whatever is the voltage coming here, will go on changing with time as the temperature or other factors are changing. So this is how we model the battery. Most of the cases, in many cases, we neglect these time constants, but if you want to have an accurate model of the battery over, say, 1 hour time, okay, you should use then these RC time constant, like what we do in a thermal system, okay. Heat sink model also has this RC time constant. It's all comes from the thermal model of the system, okay. And these are some of the references that you can use for getting your some more material on this battery. So this concludes the battery energy storage system which we have dealt in this course. Thank you.